Okay, we're back. So you've had an opportunity to do some of your independent practice on fossil correlation. Now we're going to continue fossil correlation by working on the lab. I know that you're not expecting necessarily to do a lab while you're at home, but I'm going to walk you through most of the fundamentals of this lab so you can handle most of it at home. So right now we're on page 185 of the packet, mashing rock layers. Give yourself a moment to read through the introduction. Focus on creating definitions for this vocabulary. We have absolute age, index fossils, correlation. We have some procedures here to read through. I think it would be best for you to read through them, pause and read through them. After reading procedure A, let's go to the data and images for procedure A. Okay? So outcrops from 4 locations. So we have 4 different locations. All of them are separated by a distance in between them. Right. What you'll notice is that there are no fossils in these layers. At the moment, this is just a warm-up. You are going to be purely using relative age dating. So you're going to be using your law of superposition, your law of cross-cutting to help you figure out the order of rocks for each of these locations. With that said, each location is not coherently a sequence, not needing the other ones to identify the actual order of all rock layers. So for instance, if you look at the bottom, like we always start for relative age dating, you can see the bottom has many different rock layers. At each location A, B, C, and D, you can see that these are the bottom. So these are the oldest at each location, but they're not necessarily the oldest among all 4. And so we're going to have to use our process of superposition and our understanding of unconformities to help us determine which one of these locations is actually the oldest rock layer. Okay? So let's get started. I'm going to give you an access point together here in our pre-lab. So I would take a highlighter, maybe a pen, and we're going to mark out where those unconformities are. So that gives you a little bit of a head start so you can see where you can fill in the gaps of history. So for our first unconformity, we are going to draw or highlight a line here in A. So we're 2 blocks up in location A. For location B, we have 2 unconformities. Our first unconformity is here. Our second unconformity will be here. I would also like you to recognize that in location B, this top layer that is an igneous rock is not showing contact metamorphism. That lack of contact metamorphism here, unlike in locations A and C, indicate to us that something is missing here also. That helps you find unconformities. In location C, we have an unconformity here. Okay? In location D, we have an unconformity here. So let's make sure that depending on when and how long you're working on this lab, let's create a key for ourselves at the top. These lines, these red horizontal lines, are going to be unconformities. Okay? So we have missing rock layers at each of these locations. You will see that there is a key as to the name of rocks that are over here. I will do my best to refer to those as we're going through them, rather than just saying this layer at this location. I will refer to it as conglomerate. I will refer to this one as gneiss. I will refer to this one again as conglomerate, and this one will be sandstone. So let's begin the process of figuring out which place has the oldest rock layers. So we'll get you kicked off with this. So if I'm looking at my 4 rock layers, I have to determine if any of these rock layers at any location can be found above another rock layer. Because if it is found elsewhere above another rock layer, it must be younger than the rock it's sitting on top of. Because that's the law of superposition, stating that those rocks on the bottom must be older than the rocks that are on top. So let's analyze together. I'm going to pick a place. I'm going to pick this one right here. I'm going to look at conglomerate. I'm going to see, is conglomerate found anywhere else in any other location? So as I scan across any of the other layers above, I do see one here at location C. So to me right now, location C is proving to me that location B and location D, those rocks are not the oldest rock layers. Also, another assumption we have to make here is that for our purpose in this example only, that these rocks, even though they're the same type, we're also considering them the same age. That will change once we get into procedure B and diagram B below. That will involve specifically fossils, and we'll ignore the accommodation and assumption we're making here that these 2 and 3 conglomerate layers are the same age just because they're conglomerate. Okay? That's just for this. So because I have found conglomerate above gneiss is not the oldest. So now I'm going to take a look and I'm going to see if I can find gneiss anywhere else in this diagram. So as I scan through my locations, I do not see gneiss anywhere else. So I am going to assume that gneiss is going to be our oldest layer, and I'm going to label it with a 1. Right? Now we've begun our sequence. We have begun counting all of our layers from oldest to youngest. Now we have to start looking for, is there any place where we might find a rock layer that exists between gneiss and conglomerate? Okay? So I'm going to look and see, do we have gneiss anywhere else at all to look at? So I'm going to look. I don't see gneiss anywhere else to compare to see if there's any layers above it besides conglomerate. And because I don't have any other evidence to prove that there's anything between them, I am going to assume and label that as our second oldest layer. Okay. So now we have our first 2 layers in the sequence. With that said, let's rewind back to that assumption we were making, is that this conglomerate is the same age as all the other conglomerates. So now, because that's the case, I can correlate between each of the other locations, B and D, and give them a 2 in the sequence as well. So now I know, it's a little messy there, try to keep it tight to the layer. Now I know this is the second in the sequence. So I'm going to then continue my sequence. I'm going to give you one more step to show you maybe how to deal with an unconformity. So if you look here, we have conglomerate, and then we have rock salt. And we've got this unconformity that I've given you as an access point. That means we're missing layers here. So part of what we're going to have to try to do is determine what layers might be in between them. So we might be looking at another location of the 4 locations that shows you a conglomerate and a rock salt, but there are layers in between them. So let's start scanning our locations to see if we have anything like that. Sure enough, location 2, we've got, or I should say location B, we've got our conglomerate here, labeled as the second oldest layer, and it looks like we've got a rock salt way up here, showing us that there are layers in between. Okay. But that's not going to help us just yet, because it looks like we have yet another unconformity here where there are missing layers between the conglomerate and the shell. So maybe we need to start looking and see, is there a layer anywhere else in another location that shows us that missing rock layer between the shell and the conglomerate before we choose to continue labeling. Location D. Location D, we've got conglomerate here, we have shell here, and we have no unconformity, and another layer, our next oldest layer, sandstone. So let's label sandstone as the third oldest layer within all locations. Now we have to scan to see if sandstone exists anywhere else. We have sandstone here in location A. So this is going to get you through the rest of this diagram so that you can order all of your layers. In order to complete this part A with the outcrop from 4 locations, your report sheet is going to follow on page 187 of the lab. Here you have procedure a column of blank boxes. Within these blank boxes, I'm asking you to sketch each of the layers from oldest to youngest. So you would be sketching in nice and labeling nice. So for instance, we'll get some wavy lines in here, the bands that we see in metamorphic rocks, especially in gneiss. And I'm going to label that nice. The expectation is that you'll continue this sequence until you've filled up all of these layers and have labeled them. I'll show you how to do procedure B in just a moment, so let's go back to the first page and read procedure B. Read through it thoroughly, take your time, annotate, take some notes, find your notes that came from previous fossil correlation, like your independent practice, or your other annotated notes that introduced you to this topic. Read through this. Make sure you have your reference tables available because we're going to be dealing with actual fossils which have time periods. Okay, now that you've had a moment to read through that or pause the video, let's go to here. This section below is for procedure B. So here we have index fossils of different geologic periods that we are going to utilize to figure out the order from oldest to youngest rock layer using index fossils. Okay? So here we have location A, B, C, D. Very similar to what we just had up in procedure A. More importantly, I would like to reiterate, at this point, when you see 2 rock layers that are the same rock name, they are not to be assumed that they're the same age. We have to use fossils specifically to do that. Example, here's the trick. These 2, they may be both limestone, but they are not the same age, even though they are directly across from each other. These fossils will dictate the age and period of time that they all exist in. So to get this thing kicked off, we're going to look and see we've got several index fossils, 4 of them. This one here, pecten, a crinoid, an ammonite, and a trilobite. Each of those organisms have been given a geologic time. So this one is giving you an epoch. This one's giving you a period, and a period. This is a trick. We need to figure out what period this is from so that we can compare a relative for all of these. Okay? This is kind of like you got your apples, here's your orange. Okay? We've got to make that an apple. Not that you can really do that in real life. Anyways, so we've got Oligocene epoch, to recent. So this is present day. Okay, so let's go to the reference tables. Let's try to figure out exactly what that is. So if you forget, maybe put these side by side so that it's easier for you to see the words with your reference tables. All right, so Oligocene epoch. Let's go to the Oligocene. Here is the Oligocene to the present day. For our purpose of this lab, you can choose Paleogene, Neogene, or Quaternary, whichever makes you happy, because either way, this procedure B will work just fine. So I am going to choose the Neogene. So I'm going to go back to my lab, and I'm going to refer to this as the Neogene period. Okay. Now I have the Mississippian period, Cretaceous period, Devonian period. If you've already looked at the access points, one of my guidance cues to you is to figure out what the range of time is for each of these periods so that you can start comparing which one's older and which one's younger. So let's start with the trilobite, Devonian period. So we're going to give ourselves a gap. And we're going to put it in parentheses so it's easier to see later on. But let's go down here to the Devonian. For the sake of the video, I know you have your reference tables. So if you're looking here at the beginning of the Devonian, refer back to that geologic time video if you need to, but the beginning is further in the past. So 416 million years ago, MYA, to 359 million years ago, MYA. 416 to 359 million years ago. So here is our time range for that fossil. Let's go to Cretaceous. Cretaceous period, we're way up here. So we're 146 million years ago to 65.5 million years ago. For the sake of the space that I have here, I'm going to also change colors so that it's easier for you to see the numbers, but also I'm going to remove the unit so that I have more space to write, and you can see it as well. But that doesn't mean you should leave your units off. So, Mississippian period. Here is our Mississippian. It's a subsection of the Carboniferous. So we have 359 million years ago to 318 million years ago. And then our Neogene. So I'm going to move some information over to here just because of the sake of space. You'll have a bit more room because you're writing in pencil on yours. So the Neogene. Neogene is 23 million to 1.8 million. I'm going to get an MYA there just because I've got a little bit of space to do so. All right, so we have figured out all of the ages of our index fossils, and now it's time to apply that theory and understanding to correlate these four layers. So just like the last one, we have to figure out which location has the oldest rock layer at the bottom. Pure relative age dating is not going to work, so we're going to need to analyze our fossils. So of our four fossils, we have to determine which one is the oldest fossil. In this case, it's the trilobite. So you're going to want to look for the location with the trilobite. Okay. So here's the location with the trilobite. I am not going to give that a 1 because there are rock layers beneath it. And we're doing the order of all the layers, not just the fossil layers. We need those index fossils to help us identify that place. So here we have our oldest fossil, the Devonian. So this layer at the bottom is going to be our first layer in the sequence. And continue counting up. Okay. Part of what you also need to realize is that you have an igneous. The board is not letting me write that in there, so I'm going to bring it down over here. An igneous eruption. So this is an igneous event, meaning that this is acting like an index fossil. So you're going to utilize this also to help you correlate a layer. This is the only rock layer you can do that with in Procedure B. With that said, you have multiple layers, you have multiple fossils in order for you to correlate with. So I will make sure that you understand that those fossils correlate, meaning they will get the same number in your sequence. And these fossils will also get the same number in the sequence so that you can continue finishing all of the sequence. You do not need to add these arrows to this diagram for your lab. This is purely to show you that your correlating layers will be the same. In order to finish out this particular diagram, you will be again sketching your layers with fossils. You only need to show the fossil-bearing layer once. So if there is a trilobite fossil in 2 locations, you'll only fill in one box to signify that they're correlated together and the same. You will then provide the geologic time period for that fossil-bearing layer, along with the date range in years for that fossil. Okay? Also, it is up to you to try to fill in the other periods of time in between, as we have learned in some of the other practice-independent questions. At the very minimum, I'm requiring you to try to solve the period above and below the one that has a fossil. So if you have one that's Cretaceous here, you can look up what's older than Cretaceous and what's younger than Cretaceous by one period. Procedure C is entirely a bonus. It is going to be worth 15% bonus. I'm not going to walk through this. The procedures are clear enough. A lot of it deals with unconformities. You then have your questions here to which an access point will be available to you. In order to get the full 15 points, you will also have to answer these as well. Number 8 and 9. If you have any questions, feel free to message me in Google Classroom or send a message down in the comments below here, and I'll try to get back to you, and we can hopefully all work through this together. Bye.